Hello and welcome again to my Physics Online video lecture series. In today's video, I'm going to be talking a bit about two concepts that are usually introduced with forces, the concepts of mass and of weight, and what they mean in a physics context, and how they differ in a physics context. So this is part of my series of lectures about forces and Newton's laws. We're not necessarily going to be referencing Newton's laws too much in this particular lecture, but it's a very important tie-in to these topics, let us say. So what do each of these two things tell us? What does weight tell us? What does mass tell us? Well, you will recall from my Newton's first law video that I said that Newton's first law is sometimes known as the law of inertia. And it basically tells us that if the total force acting on an object is zero, then the object will tend to retain whatever quantity of motion it has. That's another way of saying the object will not accelerate, meaning it will not speed up, it will not slow down, it will not change directions. And also it means that the object mass essentially also remains the same. So there's that word mass. What is the mass of an object? Well, mass is basically a measurement of inertia. Typically, when we're writing equations, we represent mass with a lowercase m. Sometimes we use an uppercase m, but usually it's a lowercase m. The units are in kilograms. So the SI MKS unit is kilogram, and we represent that as kg, lowercase k, lowercase g, and that is the MKS unit. You can also use grams, which is variously represented as G or GR, and that is what's called the centimeter gram second unit. That's sometimes used. And then for the imperial unit, almost nobody really goes into this. It's the slug. So this is imperial. And these two are the ones that we basically commonly use. Recall our unit prefixes mean that there's 1,000 grams in 1 kilogram. So I've said it's a representative of the inertia of an object, and that is something that will be maybe better defined later when we get into Newton's second law, or you can refer to the brief video that I've made previously about Newton's laws in general. Essentially, the more mass something has, the harder it is to change the object's velocity. So the more mass something has, the more force you have to apply in order to make the object either speed up or slow down by a given amount, or in a given time, or the more force you have to apply to get the object to give you the same amount of change in direction for its motion. So all of those things are kind of ways of saying this is what mass is. There's another way of representing mass, and that is to essentially ask how much stuff or matter or material is present in an object. And in some sense that gets to our standards for measurement. How is a kilogram defined, or how has it historically been defined, and how might it be defined? Right now it's defined by the standard kilogram. It's basically a little bar of metal that's kept in France, I believe. And then the NIST has a few supposedly identical bars of metal that they can use as standards. But it's the one that's held by in France that actually is the true standard of a kilogram. Now there have been proposals for how to define a kilogram or how to define mass separate from this. A simple idea of it is to ask what inertia is this equivalent to? And so one way of doing that is to take some pure material, carbon, for example, usually carbon 15, carbon carbon 12, and to say how much of this carbon 12 do we need to make, or do we need to have in order to make up this much mass. And so that is a different way of saying we're going to count how much stuff is in an object via counting how many protons, neutrons, and electrons are present. So protons have a given mass, neutrons have a given mass, electrons have a given mass, all at rest, of course. So how many of each of those are present in the object kind of gives us a total amount of mass. But that's also kind of inconvenient in the sense that you sure need a lot of any of those to get to macroscopic scales. And there's a separate set of videos that discuss that, along with such concepts as Avogadro's number. But you could think of mass as how much matter is actually present in an object. On the other hand, we have weight. So what does weight mean? Well, weight is actually a force. So weight is a force. Mass gives us inertia. Weight gives us force. Weight is basically variously taken. You can use like what do you get when you're standing on a scale and the scale tells you your weight? And the answer is the scale tells you essentially how much force is needed to hold you up. So how much force is needed for you to not essentially collapse through the scale or collapse into the ground. So weight is a force. It is dependent on mass. So it depends on mass. The more mass you have, the more weight. So weight is proportional to mass, but also it depends on the local free fall acceleration. It depends on gravity. The more gravity is present, the more weight you have. So this is proportional to gravity. The equation, or maybe before I give an equation, I should say what is it that we use for weight. We usually represent it via a lowercase w, or sometimes we use an FG. In fact, I actually usually use an FG. And the reason why is because in some sense, weight is equal to the force of gravity that acts upon an object. And we could modify this. We could say apparent weight is the apparent force of gravity that acts on an object. Or alternatively, the apparent weight, the weight that reads out from a scale, is how much normal force the scale is applying to you, which under normal circumstances, no pun intended, is the amount of force that gravity is pulling downward on you with. So a simple diagram for that is if you're standing on a scale and you're looking at the scale, then you have F, and you also have this scale pushing upwards on you. And this force from the scale, which we can label as Fn or Fs, should be equal to the force of gravity. Now, what is an unnormal circumstance in which this may not be the case? Well, essentially, if you put the scale in an elevator, when the elevator first starts moving up or first starts moving down, the scale reading will be off. And the reason for that is that the apparent gravity is going to be different in that elevator when you're accelerating upward or accelerating downward. So if we want to do this as a truly weight, we might say that W is equal to Fg plus MA. So Fg plus MA. Or for a system that is oriented downward, we might make this a system like this. Okay, and so basically what that means is if you're accelerating, W is equal to the mass of the person, object, or whatever times the G, and G is assumed downward, so we'll take a positive G to get the weight. And now if you're accelerating upward, then that also means that you have an increase in your weight, and if you accelerate downward, you have a decrease in your weight. So in vector form, we might say that W is equal to mass times negative of G plus A. G again is oriented downward. A, when it's positive, is oriented upward. So if you accelerate up, then weight will be greater than mg. If you accelerate down, then weight will be less than mg. With that said, under normal circumstances, what we end up doing is using weight interchangeably with mg. So that is more properly called the force of gravity. Fg is equal to mg. Now, a couple things about mass and weight that should be apparent here. If I am in an elevator and I am accelerating upward, has the number of atoms that makes up me changed appreciably? No, not really. There's still the same number of atoms in me as when I'm standing still. If I'm accelerating downward, there's still essentially the same number of atoms in me as when I'm standing still. So what this tells us is that mass does not depend upon accelerations and gravity fields and that kind of thing. If I go to the moon, then I will have the same mass as if I'm standing here on the Earth. And I will have the same mass if I go to Jupiter or Mars or what have you. If I go to the sun, then I will burn up and die and probably not have the same amount of mass anymore, but my atoms will still have the same amount of mass. If I go to all these other planets or extraterrestrial bodies, the moon, Mars, the sun, the Uranus, Jupiter, whatever, my weight will be different on each one of those. So my weight changes from one place to another. My weight changes when I get on the elevator, or my apparent weight at least changes when I get on and off the elevator. My weight changes if I am on an airplane and it goes into a sudden dive downward or accelerates upward, all of that. My weight or my apparent weight, the weight that the scale reads, will all be different. But my mass stays the same. So in some sense, weight is a property of a system, mass is a property of an object. Okay, I will say that again. Weight is a property of a system, mass is a property of an object. The object's mass doesn't change if you change where it is in the system or what system it's a part of. But its mass does, the mass does not change, but its weight does change. Let's work a few related examples to close out our video today. So we want to determine the weight of a 20 kilogram shipping container in 3 cases. First of all, when it's just sitting there on the ground. Second, it's been loaded up onto an elevator, which you've now pushed like for the top floor, and it's just starting to accelerate upwards at 0.5 meters per second squared. And third, on that same elevator, as it kind of is like gliding between floors at a constant speed of 1 meter per second. So how do we get the weight in each case? Well, in this case, the weight will just be equal to m times g. So that is 20 kilograms times 9.8 meters per second squared. So g, this is the free fall acceleration, g. This can also be interpreted as 20 kilograms times 9.8 newtons per kilogram. In this case, it's still the same g, we've just changed the units slightly, and the units now represent what's called gravity field strength. Either way, what you end up getting is 196 newtons. If you round it to two significant figures, then you should say maybe 200 newtons. Now we're on an elevator that's accelerating upward at 0.5 meters per second squared. So the weight is now the mass times this same g plus this upward acceleration. So we could say something like this, and therefore the weight is m times g plus a. And so now what we have is 20 kilograms times 9.8 newtons per kilogram plus 0.5 newtons per kilogram. This comes out to 200.9 newtons. Again, if we're rounding, this is maybe 201 newtons if we're keeping three significant figures. Okay, in the third case, we're now moving at a constant 1 meter per second between floors. So we can again say W is m times negative g plus a, but a is now 0. And so this again looks like m times 9.8 newtons per kilogram. And so once again, our weight would be 196 newtons, same as if it was stationary on the ground. I should add, though, that if the elevator was unrealistically tall, like it's a space elevator, and so you start on the ground floor and you end up 20,000 kilometers above the Earth because it's like a space elevator somehow, then this is no longer valid. So this 9.8 newtons per kilogram is valid if you're close to the ground. Even if you're like a kilometer or two above the ground, it's still pretty well valid. But if you go to 1,000 kilometers, something like that, it's no longer valid. So that is 3 related quick examples. Hopefully they help you to understand what's going on with this weight versus mass and how to calculate weight from mass. In any case, I do hope you've learned something from watching this video today, and thanks for watching.